Good morning.
Good morning.
So today I'd like to continue our discussion of the structure and stereochemistry of sugars. We're going to then talk about reactions of sugars, and we're going to come back at the end to look, if everything works out, how Emil Fischer originally determined the structure and stereochemistry of sugars in what really was a tour de force work. And I'll just give you a teeny tiny taste of the flavor of the chemistry and the logic involved. So I mentioned Fischer, and last time we introduced Fischer projections, this way of drawing sugars that really pervade sugar chemistry, and it's a very, very useful tool for quickly thinking about structure and stereochemistry. And so we're going to use that along with Haworth projections and other projections in today's talk. So I want to start by just giving an overview of how we can look at some stereochemistry of sugars. And I'll take some very simple, very small ones. We've talked about glucose. Glucose is an aldohexose. We've talked about galactose. Galactose is another aldohexose. These are 6-carbon sugars. At this point, I just want to start out to give you the simplest thing where we can get all the stereochemical relationships. And so I want us to look at various tetroses. Tetroses are, of course, 4-carbon sugars, and specifically aldotetroses. Aldotetroses are sugars where the one position is an aldehyde. We'll later see ketose sugars where you have not an aldehyde but a ketone group, and all of these are carbohydrates. All right, so to give some flavor of stereochemical relationships and maybe harken back to 51A, let me draw out the 4 aldotetroses. Now, 4 I'm going to qualify because you could also say it's 2 depending on whether we're counting enantiomers. So let's start with the natural isomers. So this sugar, this 4-carbon sugar, is D-threose. And remember, all of the D sugars, by definition, when we draw a Fischer projection this way, all of the D sugars have the hydroxy group at the carbon next to the bottom position, the bottom stereocenter, have that with the OH pointing off to the right. Remember, this representation has the backbone curving backwards, snaking backwards in a series of zigzags. And so this means this OH is pointing out of the board, this hydrogen is pointing out of the board, this CH2OH is pointing back, and this remainder of the chain is pointing back. And then in this representation, we continue to point the aldehyde group further back, and so this hydrogen is pointing out, and this OH is pointing out. Now, what's nice about the Fischer projections is we can rapidly lay out all different structures and compare them. It's quicker and easier and more intuitive than zigzag structures. And so I'm going to draw another D sugar, another D aldotetrose. So it's still going to be D, but now instead of having this, so that means this hydroxy group is still off to the right. But now, instead of having this stereocenter with the OH off on the left, we're going to have it off on the right. And this one here is called D-erythrose. And of course, these 2 molecules here are diastereomers. We talked about diastereomers last time. We talked about, for example, glucose and galactose. Those are diastereomers that differ at one stereocenter. We have a special name for a stereoisomer that differs, a diastereomer that differs at one of many stereocenters. We call that an epimer. And then we also talked about stereochemistry at the carbonyl carbon in the cyclic form, in the anomeric carbon, where you could have either the beta or the alpha stereochemistry, and we had a special name for that, anomers. So we saw beta D-glucose and alpha D-glucose, those two diastereomers, in addition to being a type of epimer, you would also refer to them as an anomer. Anyway, these are just generic diastereomers and epimers, I guess you would say. Now, imagine for a moment that I flip all of the stereocenters in the molecule. I invert them, and so we go like this. And again, I can very rapidly represent this for our 3-os example. So now, for the 3-os, I've flipped this stereocenter on the bottom. So that inherently is now going to be an L sugar. And if I flip the other stereocenter, like so, so now I've made the molecule that's the mirror image, or more specifically, the non-superimposable mirror image. I have represented the enantiomer here. And of course, that means this compound I've drawn is L3-os. Sometimes the L sugars are referred to as the unnatural sugars and the D sugars as the natural sugars.
Wait, shouldn't it be erythrols because the OH is on the left, like the second?
No, because erythros. So good question. This is why we're going through this with some care. So here, if I now go ahead and make this L sugar, this is the enantiomer of, whoops, that's supposed to be an aldehyde, so we're going to make that CHO. So this is the enantiomer of erythros, and so this is L-erythros. I saw another question.
So the bottom carbon that's next to the black.
So this is the S stereocenter, right. Now, one thing that's interesting, and we'll get to this when we talk about the Fisher proof of stereochemistry, is until many years after the relative stereochemistry, the diastereomers of sugars were determined, people couldn't tell which enantiomer was which. And so arbitrarily it was chosen. Eventually it was discovered what was real. But all of these relative stereochemical relationships in the terms D and L apply regardless of whether D is R, as we saw it was, or whether D is S. Other questions at this point? So we would say that L3-os is the enantiomer of D3-os. L3-os is a diastereomer of L-erythros, and L3-os is a diastereomer of D-erythros. So that gives us sort of a basic introduction or reintroduction to stereochemistry and shows us how we can use these Fisher projections very nicely and quickly. So I want to take us through a few other forms, a few other ideas in sugars, and then we're going to come back to some reactions of sugars. So again, there are two different diastereomers of erythros, of aldotetroses. And then there are 4 of aldopentoses and 8 of aldohexoses. And we're not going to learn or think about every sugar, but I'll give you a few as an example here. So I think in terms of the aldopentoses, I'll write aldopentose. 5 carbon sugars. The one that's got to be the most important is ribose. And ribose happens to have all of the OH groups on the same side in the Fisher projection. So I will write D, ribose. Why is ribose important? It's in RNA. Deoxyribose is in DNA, deoxygenated at the 2 position. And so this is a tremendously, tremendously important sugar. Now, we've learned to go ahead and think about the, well, let me go ahead and I'll do this on this board here. We've learned to recognize that sugars have a cyclic form, and generally, even though I've been drawing them predominantly, or been drawing them as the free aldehyde, remember we talked about how the cyclic form, the hemiacetal, and the aldehyde form rapidly interconvert. We said glucose, for example, is only 0.003% of the open form. Ditto for ribose. In water, ribose is predominantly the closed form. And there are 2 different structures, 2 different isomers that exist. One of them is a 6-membered ring isomer. And this is, and we're not going to focus, remember I said the squiggly line means mixture of alpha and beta. Beta's up, alpha's down. We're not going to focus on that stereochemistry. That mixture of alpha and beta anomers will exist in equilibrium, one with the OH up, the beta, and the other with the OH down. That stereocenter isn't fixed, it's labile. But we will focus on the others. And if you just imagine picking up the molecule and laying it down, you can see in our Haworth projection here that our OHs are going to go down. And maybe the only one that's tricky in one's mind eye to convert this Fisher projection to the Haworth projection, maybe the only position that's tricky is that next to the bottom one. And so just imagine in your mind's eye, we're going to rotate, rotate, and rotate like that. And now you say, okay, so we bring this OH down here, the CH2 comes here, and the hydrogen comes here. And so if you can do that rotation in your mind's eye, you pick it up and you say, okay, actually we're going to, I'm sorry, for this one, we'll do that next for the furanose form. For the pyranose form, we're just fine, because we just cyclize on this oxygen. So we bring this oxygen around to that hydroxy group, and so we have 3 OHs pointing down. So I was getting ahead of myself. Okay, so here's the Haworth projection for the pyranose form. And in solution, ribose exists in water. It exists as 76% of the pyranose form as a mixture of alpha and beta anomers. But the other form that it exists in is the furanose form. The furanose form is the 5-membered ring. It's the one that when you see DNA either in the chapter or in your biochemistry courses, you think DNA and RNA, I guess more specifically. So we're going to draw the pyranose form. So the pyranose form is going to be cyclizing not onto this oxygen to make a 6-membered ring, but onto this oxygen to make a 5-membered ring. So now, and I guess I'll raise this up a little bit to give me room. So now we'll draw the Haworth projection of the pyranose form. So if we look at that, we're going to cyclize on this oxygen. Well, that's still going to, as we pick this up, see my fingers here, they're pointing out. I'm just picking that up. These two oxygens are going down. Again, I'm going to leave our stereochemistry unspecified at the anomeric position because we'll have a mixture of alpha and beta anomers. Now, as I said, to get over there, we're going to cyclize on this oxygen. So we'll just bring this oxygen down, rotate this CH2 up, rotate that hydrogen over. We're just rotating about a bond as a mental operation. So when you do that, that puts this CH2OH up and the hydrogen down. So that's the pyranose form of ribose, the furanose form. Boy, I can't talk today. So let me write pyranose form and furanose form. And this is 24% at equilibrium. And you should be proficient enough, and of course this is at equilibrium in water. And you should be proficient enough to do these operations in your head that I've just done. Now, the best way to train yourself is to begin by working with models. Plastic models are a great way to go. Dig them out from 51A. Computer models are a great way to go, and I've given you those tools to start with. A little bit of imagination. Remember, I gave you glucose. Just a little bit of imagination in rotating in pi mole. That structure I gave you for glucose will allow you to see this relationship. Or, of course, you can just edit it and put in the hydroxy groups in the right place and delete it. But I've given you that linear form, which is representing our Fisher projection. I've given you a cyclic form that represents the Haworth projection of the pyranose form. So as you work through these, you will become better and better at seeing the relationship in your head. All right, all of the sugars that I've drawn thus far, all of the monosaccharides that I've drawn thus far are aldo sugars, aldotetroses, aldopentose here, and aldohexose. Let me show you a keto sugar. So remember, keto sugars are based on ketones, so we call them ketoses, and I'll show you a ketohexose. And my philosophy has been to teach you some important ones. We're not going to become sugar chemists. We're not going to master all 8 diastereomers of the aldohexoses and then all of the various possible ketohexoses. But let me give you one of them that you will know of by name. And again, I'm going to draw it as a Fisher projection. And so this looks very much like glucose, except remember, glucose had an aldehyde up on top and had a hydroxy group off to the right at the position number 2. Here we have a ketone group. We don't have stereochemistry at this position, but I have to draw the carbonyl somewhere. So we have 3 stereocenters. This sugar is fructose, or more specifically, D-fructose. You've, of course, heard of fructose, right? You've heard of it in the fruit sugar. It's in fruit. You've heard of it, alas, in high fructose corn syrup, which is produced by hydrolysis of starch. High fructose corn starch from corn. Corn is very starchy. Starch is a big polymer of glucose. And upon acid treatment fructose and glucose can isomerize to fructose. Maybe I'll give that to you as a mechanism at some point. That'd be a good exam problem. Anyway, so coming down to fructose, so fructose is a ketoisomer, and fructose exists in a pyranose form, and it's 60% in the pyranose form. And again, all of this is at equilibrium in water. That would be cyclized onto this hydroxy going to form an acetal with that carbonyl. And it's 40% in the furanose form. That would be with this hydroxy cyclized onto that carbonyl. Now remember, we've had this theme that aldehydes are more reactive. They're less stable than ketones, and we see this in the sugars very nicely. So glucose, there's very, very, very little of the free aldehyde in solution, 0.003%. Fructose, there's still not a whole lot of the free ketone in solution, but there's a good bit more. There's about 0.25% of the ketone in solution. I'll say open form. By open form, of course, I mean the ketone. All of this is in aqueous solution, so I'll write in water. And to me, in my mind's eye, that kind of gives me this feeling about stability. We saw this with aldehydes and ketones. Acetone in water is stable enough that you have very little of the geminal diol. Acetaldehyde has about 50% as the geminal diol in water. The aldehyde is much less stable because you don't have two electron-donating alkyl groups. And we see this here as well, that you have about 100 times more of the keto form, of the open form, of the carbonyl form in fructose than you do in glucose. And so again, that sort of says, yeah, aldehydes are a lot less stable, a lot less happy than ketones. All right, this introduction to sugars, and indeed this whole chapter is only going to be an introduction. This really sets us up to introduce some chemistry of sugars. And the first chemistry I think I want to introduce is the hydrolysis of glycosides. We looked at lactose as a sugar. Your body, if it does break down sugars, breaks it down into the monosaccharide units. Some people end up not being able to digest milk, meaning they don't have the enzymes to help break that glycosidic linkage to break it down, and then you have bacteria do it for you in the wrong place in your body and give you gas. All right, so I don't want us to start with a big sugar, but I want us to see another sugar. And so I'll show you another disaccharide here. So remember, I mentioned starch would be one that we can break down as well. But I'll show you a simple one. And we'll use one glucose unit and one fructose unit. This is, of course, the one with one glucose unit and one fructose unit is sucrose, so another very, very important sugar. And in many of the glycosides, you have an alpha linkage between the sugars. So starch has alpha linkages, and cellulose has the more stable beta linkage. So alpha means down. So here we have our glucose unit. And now I'm going to connect to another ring, and that ring is going to be a fructose unit. And so we have a pyranose ring, a 5-membered ring, and I'm going to go ahead and put in all my parts of fructose here. So I have a CH2OH group. Here's our anomeric position. I have an OH group off of this position going down. Remember, people often do a little broken line to show it's in back. And then I have a CH2OH group going up there. So that's a glucose unit linked by a glycosidic linkage. We call this oxygen a glycosidic linkage. Glucose linked by a glycosidic linkage to a fructose unit. Now, acid catalyzes the breakdown of glycosidic linkages. And so if we treat sucrose with acid and water, I'll write this as H3O plus. That would, of course, be a strong acid dissolved in water. HCl is widely used, although sulfuric acid in water could be used as well. Remember, consulfuric acid dehydrates sugars, but in water you don't have that. And if we go ahead and we treat our sucrose with strong acid, for example, boiling it up in 6 molar aqueous HCl, which is popular as a good way to hydrolyze a variety of different compounds, we hydrolyze the glycosidic linkage and get ourselves one glucose unit, like so, and one fructose unit, like so. Oops, and I have dropped. Oops. I have, in fact, made a boo-boo in this structure here. And I want to correct this right now. So, at this position, we have a hydroxy group. At this position, we have a CH2OH group. So just to correlate this with the structure on the other blackboard, starting from the top, our 1 position, our 2 position, that was the ketone. It's now an acetal. Our 3 position, that's the hydroxy in the middle. Our 4 position. Our 5 position, that's that oxygen off on the bottom right next, this position over here. And the last one is our CH2OH. All right, so let me finish correcting this structure. And so here's our structure of fructose. Now, I've drawn this initially as the beta anomer here, and I've drawn this initially as one anomer. Eventually, both of them equilibrate to a mixture of alpha and beta anomers. All right, one of the things about these molecules, one of the things about organic chemistry in general, is that molecules behave as their functional groups do. And if you look at the molecule of sucrose, you will see embedded in the structure 2 acetal linkages. So you will see an acetal group over here and an acetal group over here. And we know what acetals do in aqueous acid. They hydrolyze. And we know the mechanism for that. The molecule's bigger, but the chemistry is the same. And so the mechanism for this is going to involve, and I'll just sketch this out briefly, the mechanism is going to involve protons going on to oxygen, pushing apart to give an oxocarbenium ion, a leaving group leaving, and then it's going to involve attack by water. So let me summarize that. Here's our fructose molecule. And so we're in aqueous solution. And so we can imagine protons go on, protons go off in aqueous solution. And so the proton, all the different oxygens, but since we're breaking the anomeric linkage, since we're breaking the glycosidic linkage, the point at which we're set up to break that linkage is when a proton goes on to the glycosidic linkage oxygen. And so I'm going to walk you down that productive pathway, like so. In other words, protons can go on and off other oxygens, but this particular pathway happens to lead us somewhere, and so I will show you that one. So we protonate this oxygen like so. Now, that's very good, because that sets us up for this oxygen to leave and for us to form an oxocarbenium ion. You got it in your head there? In other words, we push in with that lone pair of electrons. It pushes out, pushes electrons onto the oxygen. And now, because our sucrose molecule is so bloody big, I'm going to have to take us across to the other blackboard. And so I guess let me continue here to get us to the other blackboard. I will show an equilibrium arrow, and then we'll just swing over here. And now use your imagination, and we have a molecule of glucose. Told you you're going to see a lot of glucose. And we have the oxocarbenium ion from fructose, and so I'll draw that here. And now, to complete our equation, the oxocarbenium ion isn't stable. And so to complete our equation, water can attack, and I'll shorthand things, and we can lose a proton. And I will simply say, here's our fructose structure. Thank you. Yes. Okay. And so it has been very aptly pointed out that you can do it by using this oxygen to push out fructose. Now, here's why I did it the way I did it. My way is a little more right, a little more real. Just as the aldehyde is less stable than the ketone, the oxocarbenium ion from an aldehyde is less stable than the oxocarbenium ion from a ketone because of that electron donation of the alkyl groups. And so I pushed to give the better oxocarbenium ion, but at your stage and at your learning, yes, absolutely, we could go either way. All right, so that gives us kind of an introduction, and we can see lots and lots of other chemistry. For example, and I'm not going to take you through the details of the mechanism because I expect at this point you should be able to go ahead and do this mechanistically. You've now had both this little review of oxocarbenium ion chemistry as well as all the acetal chemistry. But I want to show you a fundamental reaction. If you take acid and a sugar, so here in the previous example, we saw a hydrolysis of a glycosidic linkage. Now I want to show you a formation of a glycosidic linkage. Call it a formation of a glycoside. If we take an acid and use an alcohol as solvent, so you've got lots and lots of alcohol, CH3OH or ethanol. I'll do this with methanol. And again, of course, you can't go to Chem's stockroom and buy H+. That means you do this with HCl or H2SO4 in methanol. Now, by the exact same type of chemistry, we can form a mixture of the beta and alpha glycosides. So on the right, on the left, I have the beta methyl glycoside of glucose. On the right, I have the alpha methyl glycoside of glucose. And of course, both of these form by protonating the hydroxy group. You kick out to give the oxocarbenium ion. Like so. And then methanol can attack from either the beta face to give the beta anomer, attack and loss of a proton, or from the alpha face to give the alpha anomer. So in your mind's eye, protons go on, protons go off, all different positions of the molecule. But if we protonate on this hydroxy, we can push it out with the lone pair to get the oxocarbenium ion. And now we're in alcohol. We have a huge excess of alcohol, and alcohol can attack from one face or the other.
Speaking of the hydrogen, the
The methanol is, attacking at the carbonyl.
oh, okay.
So I was only showing it from one side or the other. So methanol attacks the carbon. We form a new carbon-oxygen bond. At that point, you have protonated methanol. You lose a proton. We're in this vast sea of methanol. Protons go on, protons come off. Thoughts? Your mind's engaging with this, right? You're figuring the mechanism in your head, and this is good. This is good because ultimately what you're doing is working through and wrestling with the motion of electrons and the formation of bonds here.
Can we reform the glycosidic linkage with the same
Can we reform the glycosidic linkage?
same mechanism? Like H, COH get protonated and get dehydrated.
In other words, can we go back?
Yes.
Can I mix 2 molecules of glucose, for example, or a molecule of glucose and a molecule of fructose and go back? In theory, great question, really important, and a contemporary super, super important problem in sugar synthesis. Now, the problem with going back is we're always dealing with an equilibrium. We added water in the hydrolysis direction. You want to take water out. And the problem is the things that take water out also react with the other hydroxy groups. Pure sulfuric acid is great at taking water out. However, pure sulfuric acid also ends up reacting and hydrolyzing the sugar. So yes, when people want to reform glycosidic linkages, they do this by something very special. It's the same idea. Rather than having a hydroxy group at the anomeric position, they make the hydroxy group into a good leaving group, something that won't go back. And then the reaction goes. They can use chloride at that position. They can use various derivatives of sulfur that often get used. It goes beyond the scope of this course, but there's a beautiful and rich sugar chemistry. And we're just getting, pardon my horrible pun, a tiny little taste of sugars here. All right, so I want to continue with our taste of sugars talking about some reactions. So in these two examples, the hydrolysis of sucrose and the formation of a methyl glycoside, we saw that all we're getting is the behavior of aldehydes, hemiacetals, and acetals. Even the anomerization was just acetal behavior. Sugars also have lots and lots of alcohol groups. And we've learned lots of chemistry of alcohols. Your textbook chose to give you a few examples, and I'm going to take you through those. There's also some nice examples in the homework problem, but there's plenty more rich chemistry of sugars. All right. Think way, way back to 51B, and you learned the Williamson ether synthesis. You learned that if you took an alcohol and a suitable base, and I'm deliberately being dicey here because there are lots of bases and lots of conditions, and I'll give you one for sugars in a second. And an alkyl halide, I'll call it R prime X, suitable for SN2. Now, what do I mean by suitable for SN2? Well, methyl is great. Methyl iodide, methyl bromide are great at SN2 reactions. Allyl, benzyl, very, very good. Allyl is double bond. It's a propenyl halide. Benzyl is benzene CH2 halide. Those are all really good. Ethyl, okay as well. By the time you get to branch like isopropyl, not so good in the Williamson ether synthesis. You go ahead and get an ether. Well, sugars can do the same chemistry, and again, with a suitable base. Some of the base chemistry is a little special for sugars. I'm going to give you an example that actually is basically one of your textbook problems and is very, very close to things that you've seen before in the Williamson ether synthesis. Suffice it to say, there are many bases. So let me take our good friend glucose here, and I'll take it as a mixture of alpha and beta anomers. And we're going to treat it with a strong base, sodium hydride, and I'll put in parenthesis excess, and I'll give us benzyl bromide, or let's say benzyl chloride as a halide. And again, we'll use an excess of that. Normally, unless I indicated otherwise, even if I didn't write excess, I would mean that you use plenty of it. Basically, your sodium hydride can pull off all the different hydroxy protons, making them into alkoxides. Sodium hydride is a very strong base. And your benzyl halide is a good alkylating agent in SN2 alkylation. So one can go ahead and cleanly, and chemists abbreviate the CH2 benzene group as BN. So you can cleanly SN2 alkylate all of the exposed hydroxy groups. And this is a beautiful example not only of the chemistry of sugars, but also of the fact that basically all the stuff you learned in 51A and 51B still works even in much bigger and more complicated and biological molecules. Now again, not trying to get too diverse, not trying to show you too many different reactions. I'll keep to things that are in your chapter. So another reaction you learned, in fact, that we learned just back in the quarter, earlier in the quarter, was that you can make an ester by reacting an acid chloride or an acid anhydride with an alcohol. And so if I take some alcohol, ROH, and I'll write it out here, acetic anhydride or acetyl chloride, and we take a suitable base like pyridine, that our alcohol reacts to give an acetate ester. And sugars have lots and lots of alcohols. And another reaction that works very, very well is to make esters, particularly acetyl esters, because acetic anhydride is small and it's highly reactive. And so again, I will take our good friend glucose. You could do this with galactose if you wanted. You could do this with mannose. You could do this with ribose. But if I take our good friend glucose and I treat it with acetic anhydride, which I'll abbreviate as AC2O, that's just that structure up there, and pyridine, which I will abbreviate PYR. Remember, pyridine is the heterocyclic base that's less basic than triethylamine because the lone pair of electrons is in an sp2 orbital and held more tightly. It's a very mild base, albeit somewhat toxic. Now we get the acetate, and we'll abbreviate that OAC. Remember, that's just an abbreviation for that. And so we can make the acetate of glucose. All right, so we've seen chemistry of alcohols, we've seen chemistry of hemiacetals and acetals. Let's focus in on some chemistry of aldehydes. So the aldo sugars have an aldo group, and if it's not tied up, if it's in a hemiacetal, that aldehyde group is available. And so just to refresh, we learned that aldehydes are very easy to reduce. When we were talking about ketones and aldehydes, we learned, for example, that sodium borohydride, NaBH4, is a wonderful mild reducing agent. Now, one of the things about sugars and solvents is, like dissolves like. Generally, sugars like to dissolve in polar solvents, water, methanol, things like that. They generally are not so soluble in things like tetrahydrofuran, which is much less polar. So methanol, water, great solvents for sugars. So I'll show you a reduction of a generic aldehyde with methanol to RCH2OH. We add hydride anion and then protonate the resulting alkoxide to give the alcohol. And so it shouldn't surprise us that sugars have some similar chemistry. And so I will take a sugar. I'll get away from my friend glucose here. We'll come back to him in a moment. So I'll take a different sugar, one that you will have, unbeknownst to you, probably have heard of. Who's chewed sugarless gum here? Okay, if you look on the back of sugarless gum, you will often see that it contains sorbitol and mannitol. Now, this sugar is called mannose, or more specifically, D-mannose. Mannose is the same as glucose, except it's epimeric at the 2 position. If we take D-mannose and we reduce it with sodium borohydride, there are, of course, other reducing agents, including catalytic hydrogenation, which is probably how this is done industrially. So if we reduce our D-mannose, we get D-mannitol, M-A-N-N-I-T-O-L. Kind of makes sense as a name. Mannose goes to mannitol. Doesn't make any sense why the common name for the alcohol you get when you reduce glucose is called sorbitol, but you will see that on your gum there is a mixture of sorbitol and mannitol. That is a mixture of epimers at this position. All right, so all of this chemistry we're seeing here really is very familiar. And in the back of your mind's eye, in the back of your head, can be this little footnote. Glucose exists in equilibrium between the pyranose form and the open form, even though there's very little of the aldehyde form. Because of that equilibrium, the aldehyde can form, be reduced. More aldehyde forms by Le Chatelier's principle, it's reduced. And eventually, all of our glucose or all of our mannose is reduced to sorbitol or mannitol. All right, so other chemistry, and this will set the stage for talking about sugar structure determination. So, when we talked about aldehydes, we learned that aldehydes were very easily oxidized by mild oxidizing agents. Even, for example, silver oxide, Ag2O, in aqueous ammonia, NH4OH, or aqueous NH3, however you like to write it, ends up oxidizing the aldehyde to a carboxylic acid. And you can do this selectively in the presence of alcohols. So it shouldn't surprise us that you can go ahead and do this same chemistry with sugar aldehydes. So for example, I'll come back to my friend glucose here. I just needed to pick some examples for today's class. So I'll take glucose, works with all the sugars in which you have a free aldehyde group. And so if I take glucose and I expose it to these conditions, so I'll write D-glucose over here, and we expose it to the same conditions, and just to save on writing, I'll write a ditto mark. Now we get the corresponding carboxylic acid. And this has a much more sensible nickname. This is called D-gluconic acid. Wouldn't expect you to know all of these names, but they're kind of fun to roll off the tongue. All right. When one does this reaction in the laboratory, and it's often done as a laboratory demonstration of this property, what happens is the silver gets deposited on the flask because you're going from silver oxide. It's acting as an oxidizing agent. You're going to silver metal. It's getting reduced. The silver metal gets deposited on the flask, and it makes a beautiful mirror of silver. The whole flask, in about 10 minutes of shaking, becomes a bright silver mirror. Well, nowadays there are lots and lots of good ways to tell sugars apart. But back in the 19th century, people had only chemical reactions and only properties. And so it was noted that some sugars, like glucose, reacted with silver oxide, silver nitrate and ammonia make silver oxide, reacted with silver nitrate and ammonia to give a bright silver mirror, and others, like sucrose, under the same conditions, I'll just put ditto, go to no reaction. You don't get a bright silver mirror. And so it really, really stands out. The sugars that reacted were called reducing sugars. So glucose is a reducing sugar. Sucrose is not a reducing sugar because it doesn't react in this reaction. And this became a common classification. If a sugar has what basically is a free aldehyde group, in other words, it's a pyranose or a furanose in equilibrium with an aldehyde, then it reacts. If, on the other hand, like sucrose, all of the aldehyde groups are tied up by an acetal linkage, in sucrose it's just one aldehyde group, then it doesn't react, and that would be called not a reducing sugar. And so this test, this silver mirror test, got called the Tollens test after the inventor for reducing sugars. All right, so one of the themes, and we'll see this for the rest of today's lecture, one of the themes of organic chemistry historically has been, what's the stuff of life made of? What are the molecules that make up the food that you eat? What are the molecules that make up your skin, your hair? We now know starch and cornstarch and in wheat bread is an oligosaccharide. We know that it's made up of glucose units. And we know that the proteins in your hair and your skin and your arm are all made up of amino acids. But the end of the 19th century, the beginning of the 20th century, this was when people discovered that. And so the chemistry we're seeing now, and some of these questions like categorizing, is a sugar a reducing sugar or not, is part of that understanding. So I want to show you a couple of more reactions and go somewhere with it. So I'll give you two more reactions of glucose. Now, aldehydes are very, very easy to oxidize. And so there are lots and lots of oxidizing agents that can oxidize a reducing sugar. And another one is bromine. Another one is copper, copper 2 or copper 1, I forget now. That's the Felling test for sugars. But bromine is another one from your textbook, and so I'll just show you that. Bromine can also take glucose to gluconic acid, so just as we did with the Tollens test. Now I want to show you another one, and then we're going to go somewhere. So again, I'll take my friend glucose. And now we're going to treat it with a different oxidizing agent. This is a really neat reaction. We won't talk about how this occurs. We're going to take this with nitric acid in water. Your textbook doesn't mention heat, but usually you do this with boiling waters. In boiling water, so you do it at 100 degrees. Nitric acid is a good oxidizing agent. It's not surprising that the aldehyde group ends up getting oxidized to the acid group. And it's probably not surprising since we've seen lots and lots of conditions that don't touch alcohols but do touch aldehydes. It's probably not surprising that the remaining alcohol groups in the molecule remain intact, with one exception, and that is the primary alcohol group also gets oxidized to the carboxylic acid. And so now we've transformed glucose at the top end and the bottom end. And again, things have funny names. This compound here is called D-glucaric acid. And again, I wouldn't expect you to know this. These names just are fun to say. What is fun, what is interesting, of course, and what we want to pick out in picking out the forest from the trees here, is that it is a diacid. That is a molecule with 2 carboxylic acid groups in it. All right, so I want to now take us back to the beginning of the lecture. Now, at the beginning of the lecture, we started with the aldotetroses. And I drew out the structure of the two d-aldotetroses. And I know people say organic chemistry is about remembering things. It's not. It's about thinking. We've seen mechanisms, protons. But now I'm going to ask you to do something. I'm going to ask you to forget something. Forget which aldotetros is which. And more, get into the Wayback Machine when we didn't know which aldose is D-threose and which aldose is D-erythrose. Get back into the Wayback Machine when we didn't have IR spectrometers and NMR spectrometers to look at things like functional groups and coupling constants. People could burn molecules and measure how much carbon dioxide was produced and how much water was produced. You could figure out the empirical formula that way. And people knew the colligative properties of matter and knew the freezing point depression and could figure out the molecular weight that way. But you couldn't directly ask questions of stereochemistry like you can now with an NMR spectrometer telling you a cisalkene from a transalkene. And come back to the roots of organic chemistry where the question is, what is the stuff of life made from? And put yourself in the laboratory of Emil Fischer, who won the Nobel Prize in 1902 for his work with sugars. His name permeates not only the Fischer projection, but the Fischer esterification, and also a synthesis of proteins, of peptides, that interested him after he tackled sugars. He was going after all of life. He also got some of the nucleic acid bases. And so now we look at what you could do then, and you go back to the time of Louis Pasteur and tartrate and optical activity and Lebel and understanding that carbon was tetrahedral and understanding the origins of optical activity, and only being able to measure whether light is rotated, plane polarized light is rotated, and how much it's rotated, and melting points and formulas. And you ask, what are the structures of all of the 8 aldohexoses, the 4, I should say diastereomeric aldohexoses, because of course when you throw in an enantiomers there are 16, the 4 diastereomeric aldopentoses, and the 2 diastereomeric aldotetroses. And we'll just ask the simple question for the aldotetroses. Fischer extended this all the way up. So let's look at what you could do. All right, when you take one aldotetros and you treat it with nitric acid and water and heat at 100 degrees Celsius, you get an optically active diacid. The diacid, and I'll draw the structure in just a second, is called tartaric acid, the diacid in which you oxidize the upper and lower position. And when you take the other aldotetrose and you subject it to the same, you get a diacid that doesn't rotate plane polarized light, that's optically inactive. All right, so let me go ahead and draw using Fisher projections. Yeah?
The other aldotetrose, is it in the same conditions?
Oh, yeah, ditto mark. Same conditions. All right. So let me write the two structures here of two diacids. Which of these molecules has a plane of symmetry in it? The one on the right. There's a plane of symmetry here. Molecule that has stereocenters but has a plane of symmetry is a meso compound. It's optically inactive. Diacid with 2 carbons on either end, 4-carbon diacid and 2 hydroxys in the middle, is called tartaric acid. The structure on the right then is meso tartaric acid. And the structure on the left is optically, so I'll write optically inactive up here for the one on the right. The structure on the left lacks a plane of symmetry. It's optically active. I'll write optically active over here. And this particular molecule is called D-tartaric acid. Found in grapes. It's the structure that Pasteur was able to resolve enantiomers from. Okay, so now we have a little logic problem. Your textbook gives you tons of logic problems. I've tried to cut them back on the homework a little bit because I think they go a little nuts on it. This is the history of sugar chemistry they're giving you. All right, so that means if the one gives an optically active product, the structure of that aldotetrose had to be this. And so this, the one that was called threose, then Fisher knew was this structure. And the one that was called erythros Fisher knew was this structure. And that's pretty smart. All right, now I will show you the real genius bootstrapping of Fisher, and we'll introduce one last reaction. And that is the way that Fischer could bootstrap himself up to all of the aldohexoses, starting with a very small molecule. And so what I'll introduce finally is the Kalyani-Fischer synthesis. Your textbook introduces the vol degradation, the opposite, and I'll let you read about this. But I want you to see the forest from the trees. All right, so how do you bootstrap yourself up? How do you build up the sugars? And then hence, how do you go ahead and puzzle out all the stereochemical questions of the aldotetroses, the aldopentoses, and the aldohexoses? And ultimately, how do you really answer what the stuff of life is made of? So Fischer started with diglyceraldehyde. And all the chemistry now you have, in fact, you have all the chemistry you need to get up all the way to the aldohexoses, although you won't. If you take an aldehyde and you treat it with hydrogen cyanide, we already learned what happens. You form a cyanohydrin. And you do so in a non-stereospecific fashion. In other words, you get both diastereomers. So we formed a carbon-carbon bond. We've introduced a nitrile group. Now we've learned lots and lots of chemistry of the nitrile group. We learned that the nitrile group was in the carboxylic acid family. We learned that under the right conditions, you could, with, for example, aqueous acid, hydrolyze the nitrile group to the carboxylic acid group. We also learned various conditions for reduction of nitriles, and one of those conditions is catalytic hydrogenation. So imagine now that we go ahead and we carry out catalytic hydrogenation with hydrogen and palladium. Palladium's a catalyst, but you can attenuate the reducing ability of palladium by poisoning it with a heavy metal. You learn this in the reduction of alkynes with Lindlar catalyst. Palladium can be poisoned by metals like lead and barium, heavy metals that reduce its ability to hydrogenate, that attenuate it. And so if we have palladium on barium sulfate and you do this in water, you end up reducing the nitrile groups down from the nitrile/carboxylic acid oxidation state, that +3 oxidation state, to the aldehyde oxidation state. Remember, carboxylic acids are +3. It's the highest oxidation state you can go without getting to the carbon dioxide oxidation state. So you reduce the triple bond to a double bond, and you get, and I'll come to your question mark here, what will inherently be your implicit question mark in a second. And so you bootstrapped your way up one carbon to erythros and threose, or threose and erythros as I've written them on this blackboard. And so Fischer could start with one molecule. At the time, he didn't know the absolute stereochemistry, but he could start with a molecule of diglyceraldehyde and convert it to erythros and threose, which he could then tell apart by their optical rotation properties upon oxidation. And he could bootstrap himself up to the pentoses and so forth. So the one question here you probably have is, wait a second, where'd that nitrogen go? Well, the primary imines are not stable. And so in water, under the conditions, your textbook shows acid, that's fine too, but honestly in water they hydrolyze. In water, the imine hydrolyzes to the aldehyde. And so the sequence of cyanohydrin formation followed by partial reduction bootstraps you up a level. All right, well, I think this is where I would like to end up. We have now had all of the basics of sugar chemistry. You'll get some more exposure through the homework. We'll finish off our final week talking about the chemistry of peptides and the chemistry of organometallic reactions, and we'll just get a little taste of that chemistry from chapter 28 and chapter 26.